So we have a lot of different diagnostic tools we use in imaging. And the most common to everybody is an x-ray. You get your teeth x-rayed, you get your bones x-rayed if you're really unlucky. But an x-ray is a very simple thing. You have x-rays going through the body and it shows density only. Then we can take that further to a CT, which is essentially a ring of detectors, much like a PET instrument, except the CT is only x-ray and it's showing only density, but it gives you better spatial resolution. Then we go to MR. MR is different from a CT because it shows anatomy, but what it shows also is it shows the water molecules. And so mostly it's used for looking at flow, for perfusion with exquisite spatial resolution. And we can look at the brain in amazing detail with an MR and look for breakdown of the blood-brain barrier. We can look for leaks, for stroke, things like that. PET can do this also, not quite with the same resolution, but MR is really the tool for clinically using that. For PET, you may want more quantitation than MR can give, and you might do water for flow and do a very quantitative type study, especially looking at the kinetics of blood flow. But PET is unique in that with PET, what we're looking at is physiology and function. And for the most part, MR can't get beyond the blood-brain barrier, or beyond the blood barrier. Mostly it's an intravascular tracer. What we can look at is processes that go from the vasculature all the way through the interstitium into the tissue and what process we're probing. And we have enough time with PET to be able, and with nuclear medicine, but PET's a little more quantitative, what we're able to do is look at what happened where through time. So we get a kinetic curve. We don't always use the kinetic information, but over time what we can get is better signal to noise because we can separate out the transport processes from the process that we're looking at. What we can do is we can actually look at the body functioning with exquisite sensitivity with PET, and that's what makes it so exciting. It's a hard technique, but it's still, you cannot do what you can do with PET in vivo in a human with other techniques. So how do we make these radionuclides? You can make some radionuclides using a nuclear reactor. And those are reactions where you actually force, or you have a neutron go into the nucleus and make it unstable, and then the nucleus changes and becomes a new nucleus. And this is actually pretty easy if the neutrons are going slowly, because, and we call them thermal neutrons, because nuclei are charged. They're positively charged, but a neutron is neutral, and so it can get into the nucleus without having any kind of coulombic interaction or charge repulsion. But what happens when we want to do and make a different kind of radionuclide, one that has an extra positive charge like we'd need for making a positron emitter? Then what we use is an accelerator. And the accelerator started out with the old Van de Graaffs, where they make a long one, not like the one you saw in the museum, but essentially the same idea that the museum where, you know, you put your hands over it and your hair stands on the end and all your friends, a lot of charge on it. But accelerators, what they do is they give more energy to a particle. And then that particle gets smashed into our target materials to make a new radioactive type of radionuclide. And we plan this. We actually figure out what the reactions are. And what happens is we know enough about nuclear structure, we know enough about nuclear energetics especially, that we can make plans to make something and say, okay, I'm going to want this product radionuclide. And you can figure out the energy of that. And then you can say, what could I use to make that? well, how many neutrons and protons are there, and how many protons will we add? And we just do an algebra equation and say, okay, I'm going to take a hydrogen atom, or I'm going to take an alpha particle, which is helium, and I'm going to shoot it into this nucleus. And this nucleus had a molecular weight of 32 and 16 protons, say. And I'm going to add 2 and 2 on the top, so now it's 34 and it's 18 below, and then I'm going to have a particle out, and I can predict sort of what particles will come out and get my product. And so it's just algebra. And we actually have tables that show it, but what we know is that when we make radionuclides, if we shoot something energetic into it, it takes about 10 to 12 million electron volts of energy in the particle per particle out. So we build these accelerators. And these accelerators, the most common one that's in use now, they can be linear or they can be circular, but circular is the most popular if you're not doing high energy physics. And even today with the really high energy physics, they go circular because of space that's needed to make them. And the way they work is you have a magnetic field. And I'm going to talk about a cyclotron. So a cyclotron is a big electromagnet, and it has a vacuum chamber because we need to have whatever we're making not interact and go away before we can use it. And what you do is you put a little gas, and usually it's hydrogen or helium up, or deuterium, up in the center of this vacuum chamber that's within this magnetic field. And then you put it across a voltage or some method called an ion source, and it makes it into a charged particle. And you can make it positive or negative. Usually we use negative now. And most of the time we make, and I'll be specific, hydrogen minus for our field. But you can accelerate big particles if you want to. And what happens in that magnetic field is the particle is precessing depending on the magnetic field. There's an orbital, an angular velocity that's related to the magnetic field and the charge on the particle and the mass of the particle. And it's independent of the other forces we put on it. So then what we have in there in a cyclotron is called Ds. And they would be straight in a linear accelerator. But the Ds are RF cavities. And what happens is we have, let's say, a negative particle. The D, as it's in this little orbit, the D will be positive, and it'll get attracted to it. And as it gets attracted to it, it gains kinetic energy. And then it'll drift a little ways, and just as far, we know the orbital frequency. And as soon as it reaches toward the end of the D, which is got tips in a hollow cavity, it changes from positive to negative, it gets repulsed, and it starts having a little more kinetic energy. It's going faster, but with the same frequency. And so then the next D, and now it used to be 2 of them, so they were called Ds. Now they're typically more sectors, they're 4 or more. It just goes plus minus till this thing's going faster and faster and faster. And since the frequency is the same, the orbit is bigger and bigger and bigger. And depending on the charge, it goes one direction or the other. And so what happens is we go at millions of hertz, megahertz. And we do this until it reaches the end of our cyclotron, the end of our magnet, and then we change the charge of the particle. Or we could deflect it with a magnet. And when we change the charge, if it's going this way, it suddenly goes this way. And at that end is where we place our material, our target it's going to hit. And it goes through a little teeny window. It's going so fast, doesn't even notice the window loses a little bit of energy, and it slams into this material, our target, and we make new radionuclides. And that's a cyclotron. And that's the basis of what I do.